Okay, let's look at metal oxide semiconductor field effect transistor. That's a long name for it, so what we always say MOSFET. Now in the previous videos we looked at JFET, junction field effect transistors. The truth is MOSFETs are the most used transistors today. So they are the most used ones. And why? One, easy to manufacture and use. And use. Two, they are very small, much smaller than bipolar junction transistor. When you say very small, how small? Dimension wise, roughly in the like 10 to 15 nanometers. Just to give you a little perspective there, you can fit roughly approximately 4,000 transistors, MOSFET, in a space as wide as a human hair. That gives you an idea how small they are. The third assumption we're going to make, and you'll see that in a minute why, we always say no current or almost zero. No current. It's not really no, but it's negligible current. No current, so I'm going to say no, but it's very small, flows in/out of the gate. And I think the fourth reason why people like to use it or use them, high input impedance. So if you measure the resistance of MOSFET, it's somewhere between 10 to the 12 to 10 to the 14 ohms. That's in trillions ohms, infinite. So that's the reason why they are really heavily used in the industry. Now, let's look and see how they make them. So to make a transistor, a MOSFET, we take this, it can do a P-type, N-type. So I'm going to stick with P-type material here. We're going to take a plate, a semiconductor, positively charged, we'll call it P-type here. And this actually material is called the substrate. And we take two negative materials and plant them here. There's one here and charge, and there is another one here. And if we attach like a little attachment here to the end piece, and there's one here. One of these ends is going to be the drain, and the other one is going to be the source. So I'll make this one the source, and this is the drain. Now, we're going to take a silicon oxide, thin layer of silicon oxide. And that's SiO2. And if you don't know what that is, that's like having a thin layer of glass. And we put it right there over this end. and it's going to go right over this. And it's going to go right over this. That's my SiO2, my silicon oxide. And now we attach a metallic plate right here. That's made out of metal here. And now this is my gate. As you can see, actually, the gate does not make contact with the negative or p-type or the n-type. There's no connection between them. So that's why we said the current coming in or going out is almost zero. So negligible current actually flows even when the gate voltage here is positive. Negligible. So now MOSFET can be broken down to two types, well actually four types if you want to be technical. One we call the NMOS, the other one the PMOS. Negative and positive. And they also can be broken to, they can operate in two modes. One is called the depletion mode, and the other one is going to be the enhancement mode. So they can be here. You can have an NMOS depletion mode, you can have an NMOS enhancement. Most common NMOS depletion out of these two, depletion. Enhancement, you can have an NMOS, PMOS here. So what's the difference between them? First, let's talk about the NMOS versus the PMOS. What does that mean? The name NMOS came from really N channel. Negative channel. What does that mean, negative? In this case, electrons, which we know that's a negative charge, that's why it's called N channel. Electrons are responsible for the flow of the current. In a few minutes we'll discuss them in depth there. So that's with the NMOS. The PMOS, that's positive channel. So it can't be the electrons, obviously, because it's positive. The holes here, which we're talking about positive charges here, because the holes, that means they lost an electron, are the ones responsible for the flow of the current. For the flow of the current. I wrote the word that twice here. So that's the difference between NMOS and PMOS. We'll look at them shortly in depth there. I wrote the word that twice here. We said also transistor can be, or MOSFET can work be in depletion mode, or they can be enhancement mode. Depletion, when you hear the word depletion, That means the transistor, or the MOSFET, is on by default. It's going to work like a switch that's already connected, closed. It's on by default. And when you applying a gate voltage, will do what? Reduce the current, but instead of the word reduce, we use depletes the current, and that's where the name came, depletion. Depletes current. When we're talking about enhancement MOSFET, we look at the MOSFET in the off position, which means open switch. So in depletion mode, we treat the transistor or the MOSFET as an on position, and that voltage actually gonna drain the current or reduce the current. This one is gonna be, MOSFET is in the off position by default, and applying gate voltage here, does what? Enhances the current. And that's where the name came from. So let's draw a picture and go through it and see what will happen. So I'm going to look at the depletion mode first, and now we'll talk about maybe N channel, but I'll just explain depletion mode in general there. So depletion mode, DMOS. So in depletion mode, we always call that D-MOSFET. That means depletion mode. The D stands for depletion. But you'll see the word DMOS. That means you're in depletion mode. So if you picture that MOSFET looking like this. So there's the P-type here. This is the N. This is the N. And we have that silicon dioxide plate right here, and on top of that we have the metal plate, which is the gate. So if we attach the gate now to a voltage source that's positive, negative, and let's call this VGG. This is the source. I'm going to attach to ground. This is the drain. And I'm going to attach it to another voltage source, VDD. Notice this is positive, negative, where this one negative, positive. I drew the picture a little bit wrong here. Negative, positive. Let's look at that scenario, then I'll flip this one and see what will happen, plus to minus. Now, what this voltage is going to do, VDD, is going to force free electrons. Remember, this is going to be negative here. This is going to be positive. Electrons have what charges? Negative. They don't want to be next to this one. Is going to force these electrons to go up there. So this VDD forces free electron to flow from the source to the drain. As we said, I made this one really big here, but that channel is very small. So through that small channel, I made it big here just to show you. Now, the more negative that we make this, the gate voltage, what will happen if you make this negative? The smaller the drain current. Why? We narrow that area. That becomes smaller and smaller. And if you start increasing this voltage, keep increasing it, this area will get smaller and smaller. So if you watch this one, that channel here, it will start to look like this. Smaller, smaller, so you try to squeeze through that. Eventually it's going to be a voltage here where they'll allow zero current to go through that. So the voltage that allows zero current. So if VGG is negative enough, then what will happen? The drain current will be equal to zero. And that voltage is called V threshold. And anytime you look at the data sheet for any transistor, that V threshold will be given to you. So if VGG is the voltage here below or larger than V threshold, or negative small enough. So for example, right now, this is what we're looking at. If you were to graph the current. If you're looking at VGG here, and this is I sub D. If this is V threshold, there is no current going through that. Once your value is below that number, nothing going through it. If the value is bigger, then start to increase like this. The current start to flow through it. The smaller that value, the more current gonna go through it. Remember what I said about that depletion. This one is going to work as it's on by default. Applying a gate voltage decreases that current. So as we apply this one, that current gets less and less and less. So when there is no voltage here, which is zero voltage, you have a lot of current going through it. So it's open. But as you start applying that voltage, negative on the top, plus on the bottom, as you increase that number, increase like absolute value of it. Because -4, it's not mathematically bigger than -3, but the absolute value is. So as the values start to get larger in this direction, that current starts to decrease till it hits zero. And there's nothing going to us, cutoff voltage. So when you're to the left of this, when this value is below this number, that means you're in cutoff region or mode. And now what happens if I put a plus voltage on the top, minus on the bottom, instead of the reverse of that? So if we take a MOSFET now, and again, this is my thin layer here, and this is my gate right at the end of it. This is my source. Attach that to the ground. Attach this plus minus VGG. That's the drain here. Plus minus. That's VDD. So what will happen when you put a plus voltage here at the gate? The positive voltage of the gate here increases the number of free electrons. So the number of free electrons will actually increase there, going up there. The more positive the voltage here is, the greater the conduction from the source to the drain. So the larger this number, the voltage, the more current is going to go through that. So it looks like when you look at this, when the voltage is negative, where was it? When the voltage is negative, it behaves like JFET. But in JFET, you can't put a plus voltage on the top. Here, you can do that. And what will happen to my current, if you watch my current actually, let's see what my current will look like. Picture of it. I'm going through our book. And it shows the current looking like this. VGS. This is VT, threshold voltage, TH. This is VDSS, ISIP DSS, as we discussed that last time. That's in JFET. So when the value is negative, it's going to look the same, but when it's positive, you got more current going through it even. Why? Because the equation for the current, I sub D, is still the same. Is equal to I sub D SS times 1 minus VGS over VGS of squared. That equation doesn't change. And when VGS is negative, this ratio becomes a positive number, so you get a current that's less than I sub DSS. But what happens when VGS becomes a plus? Because that's a negative number here. When that's a plus, this is a plus divided by a negative, that's a negative. 2 negative is going to make it a plus. So now your current will be more than I sub DSS. Just to show you mathematically, in case you're struggling with what I just finished saying here, if we pick a value, let's assume here VGS. Usually VGS is the opposite. Let's say it's negative 2 volts. And not VGS, VGS off. That's the threshold voltage. Let's say it's negative 2 volts. That's the value that will make it no current going through it. So now what will happen to this circuit if, I'll give you some number for I sub DSS. Let's say we have a 10 milliamp. Let's look at that equation. Let me just write that equation so I don't have to slide the paper up and down. So let's use this circuit. If VGS equals, negative 1. So we're talking about right there. Notice my current is going to be less than I sub DSS. Maybe half of it, a third. Let's see what the math said. Then I sub D is going to be what? I sub DSS, which is I'm using 10 milliamp, 1 minus negative 1 over negative 2, that's a half, square it, that's 10 milliamp, that's a half. 1 minus a half is a half squared, that's 1/4. So I'm getting actually I sub DSS over 4, which is in this case 2.5 milliamp. What will happen if VGS is equal to 0? I sub D is equal 10 milliamp. From the picture, that should give me I sub DSS. And what do you know? It's 10 milliamp. That's I sub DSS. And again, what will happen if VGS now is greater than 0? So let's pick a value bigger than 0, like a 2, plus 2, negative plus 2. Let me make sure you can see the plus, because we get talking about positive value. So again, you couldn't have that in the JFET. So let's see what will happen to I sub D here. It's going to be 10 milliamp, 1 minus 2 divided by negative 2, that's a negative 1. 1 minus a negative 1, that's 2 squared, that's 4. 4 times I sub DSS, which is 40 milliamp. And notice right there, like when it's 1, way up there, the current. So that's how we calculate the current. When you are in this mode to the left, sorry, I had to send a text message. When you are in the left in this mode, that's called the depletion mode. And when you're in this mode, that's what? The enhancement mode. Now, as I said, MOSFET almost identical to JFET. Really, the major difference is enabling VGS to be either negative or positive. That's the only difference between them. Negative or positive. Now, how do we draw a picture of an N-channel D-MOSFET? The symbol for N-channel D-MOSFET, it looks like this. The drain, and this is the source. And the gate is like this. Notice we used a solid line here, not a dotted line. we use a solid line to indicate this solid line here, to indicate it's on. Because if you have a voltage source here, VCC, and you have a resistor R, and you have a wire there, then we have current going through it. You also notice we have the arrow pointing to the left. Most of us, most engineers are lazy. We never really connected. We don't put the G with the L shape like this. Oh, that's too much work. Now, the P channel, D-MOSFET, it has very similar shape. The drain, same thing, except we have the current coming out of it, the source and the gate. And again, notice we use the solid line to indicate it is on. Now in the next video, we're going to talk about the enhancement MOSFET. And we'll go through them, explain how they work. In a few minutes, we'll take some examples and go through them. So I'll stop this video here, and I'll see you in the next video.